Okay, on to question 2, which is a physical media question. So here we really just need to like read the format really well and make sure we understand what's supposed to be happening. So normal voltage is 0 volts. A 0 bit is 4 volts. So anything at this level is going to be a 0. A 1 bit is an 8 volts, so anything at that level is going to be a 1. This is not always going to be the case right there, the return to 0 ones where you're sort of looking for a shape. But for a non-return to 0 signal like this one, we can sort of label the voltages as what the bit value is. And make sure you do that because we do switch it around on you. A start bit is a single 1 bit, and a stop bit is a single 1 bit. So we're going to see the same value, one start as a 1, and one stop as a 1. So we're going to have an 8 volt to start it, and an 8 volt to end it. And then data bits are a decimal number transmitted in reverse order. Least significant bit follows the start bit. And the following waveform is generated by the system. So we know that normal voltage is 0 volts. So as soon as it goes high, and we have these nice little dividing lines that sort of show us where the bits are. Otherwise, we would need to be told like how long each bit is. But given the way that these problems usually work, we can label this as a 1 because it's at 8 volts. We can label this as a 0 because it's at 4 volts, another 0, another 1, and another 1. We know that a start bit is a single 1, and the first thing we see is that start bit. So this is not part of the transmission. We've then got 4 data bits. So this is D0, D1, D2, D3. And I'm going to write them that way because then we're going to have this, 3-bit sequence. So that's D1, D0, D1, D2. And then this is our stop bit here. And so our actual value is going to be in the order D2, D1, D0. And we're going to write those out in that way. So we can either sort of write this out 0, 0, 1 and then flip it, or we can sort of do it this way where we write the bit values from left to right and then just sort of write them under the number that they correspond to. And then this is our value that we got out. So we labeled all the bits there. We labeled the start and stop bits. And then the decimal number that we get out of this, this is binary, so we'd want to translate that to a decimal value, which this is just 0, 0, and then this is 2 squared, so this should be 4 is what we got out of the system. So again, really just reading the protocol, understanding what's supposed to happen. I made a mistake there and forgot about the 3-bit part of this, but make sure we're sort of marking off the bits as the system tells us or as the question tells us to do, and you should get full credit. So then part B, the whole transmission, all 5 bits takes 2.5 microseconds. What's the bit rate of the system? So bit rate, RB, is bits per second. So we're just trying to translate to that, right? So we've got 5 bits per 2.5 mus, and we want that to be in bits per second, right? So we're just effectively dividing 5 bits divided by 2.5 microseconds, and that should give us 2 megabits per second. So that's our final answer is 2 Mbps. This is really just plug it into your calculator, make sure you're using 10 to the negative 6th for microseconds there. On to part C. So this is asking us to draw a new waveform if the same decimal number was sent again, but using the following protocol. So normal voltage is 0 again. So we're going to start off here before we send anything, right? A 0 bit is a 4 volts. A 1 bit is a negative 4 volts. So this is going to be a 1. This is going to be a 0. It's bipolar NRZ, so we're not going back to 0 each time, right? But do be careful of that. If it says RZ, we should be returning to 0 in the middle of the bit. A start bit is a single 0 bit, and a stop bit is a single 1 bit. So to start, let's just kind of write out the same transmission that we have here. We're going to have start, D0, D1, D2, and then stop. And then we're going to go back to our normal voltage on the line at 0 after the stop bit. So our start bit is a single 0 bit. So let's go ahead and draw off a single 0 bit there. And then we're going to send the same values for D0, D1, D2. So those were 0, 0, 1. So we should have another 0, another 0, and then a 1, which is going to be this low value. And then a stop bit is a single 1 bit. So we're going to be there again. And and then we're going to go back to our normal voltage. So really just, again, following the protocol, making sure that we sort of write down those same bits that we had before. In part D, a new transmission scheme uses a parallel communications with 5 parallel channels, each channel having the same transmission rate from part B. What is the new transmission rate of the system? So this is a simple question. It's just we had 2 Mbps for each channel. We're multiplying that times 5 channels, which is now going to be 10 megabits per second for the whole system. So that's it. Just multiply times the number of channels and you're done. That's it for question number 2.